So it looks like we're live on YouTube. We'll start in just a minute. So hi everyone. So let's get started. So welcome back to the second to last lecture of the Data Mining class for this semester. This lecture will mostly will mostly be on PageRank. Let's quickly look at the schedule. So this is you can see we're almost at the end here, second to last lecture on PageRank. Then Wednesday we'll give the last lecture. This lecture, so I'm gonna try and, if I get through it, I'll try and cover part of MapReduce in this lecture, and then we might touch on some of it on Wednesday, but the main focus will be on understanding these communities and kind of clusters and other ways of defining these groups on these large graphs, say formed by things like social networks. So if you see in the stuff that's due soon, the final report is going to be due on Wednesday. So I've got a slide on this to discuss what to do. So I'll come back to that in just a minute. So there's a homework out for graphs, which is going to be due on Wednesday, April 22nd. So that is like the reading day. You should be able to do most of that now. So based on the lecture on Markov chains. So there were some technology issues, but I redid the full lecture of that, and that should be online, or a bunch of you saw the version live. So, and then the rest of the material for that should be covered in the lecture today. Then the end term test is going to be a week from today. It's going to be roughly on that day, although I will post the PDF for the end term online. So Sunday night by 9 p.m. on Sunday night, and let's see up here, and it's gonna be due by like Tuesday morning. I think I set deadline like 2 a.m. You should find it's supposed to be taken during class, but you're welcome to take it anytime in that period, but you should spend 80 minutes on it, right? So it'll be basically the same structure, the same sort of tests I would have given if it was in class, but it's going to be, it's going to be a take-home test instead. So I posted the rules for this, and there's some discussion on Canvas about this. So because it's take home, I won't be able to proctor it. Your base going to be on your honor, so not to cheat. So basically, you should spend 80 minutes on it. Again, like most cases, most of you will finish within 80 minutes. Don't communicate with anyone else. If you have a question, you can email me or the TAs for questions about stuff. I'll try and post, if there are common questions, I'll post them on Canvas so you can check stuff there. You can use basically resources from the class. I don't want you generally searching on the internet in case there's someone's asked a similar question and someone posted an answer. Please don't do that. but you can use any linked material. I could have had you made a sheet, but and that might still be helpful, but instead kind of look at the stuff in the book. You can use the search function in the PDF of the book. And then if you're aware of anyone else trying cheating, because this is on your honor, you're also bound to, to tell me about it. So if you reach out to someone about cheating, you're putting them in a weird situation where they are now bound to actually contact me. So, I assume most of you, hopefully all of you, aren't going to cheat, which is great, but you'll have to sign this in order for us to grade the test. Okay, and try and upload in PDF by scanning it or taking a picture, doing a phone upload, something like that. But if you have trouble doing that, I'm acceptable to other formats, but that'll make it easier for us to consistently do the grading on it. Okay, and then let's see, we're still going to do a poster session for the class. Poster outlines will be due on roughly on the day of the interim test, and these are just we'll give you feedback on these posters. Then we'll do a poster day during the day of the final exam. We'll send out some more details of this. We're going to try and do the whole thing over Zoom by posting the PDFs of the poster online. It used to be in a public hallway. Now it'll be in a public forum. I think we'll get something like this to work. In the past, this has been a really kind of cool experience for everyone. Everyone has liked it a lot. So we'll try and recreate it. I'm hoping we can get like 75% as good as the actual poster day. But I think it'll be actually easier on the actual students as far as going through and see everything. So I'll say more about that, the plans for that, at least in a lecture on Wednesday. Okay, so this is the main kind of schedule for the rest of the semester. Let me look at the slides. I have a slide on the final report, which is due on Wednesday. Okay, so this final report will be at most 4 pages per student. Okay, so if you have a group of 2 students, that means you get 8 pages. If you have 1 student in your group, that's 4 pages. If it's 3 students, it's 12 pages. This is an upper limit. It does not need to be, it does not need to be that much. Right, try and don't have really tiny margins and really small font. I think I set a lower bound on the font you can use, but feel free to make it larger. Okay, I'm going to be reading all of these, and I'll do my best. I think I do a pretty reasonable job, but the easier to make it is for me to read, the happier I'm going to be when I'm assigning a grade on these reports. Basically, the way these reports work, typically, if you do kind of what I expect for the project, you've kind of fulfilled the feedback that I gave you on the intermediate report. These are worth 50% of the project grade. The reports are, I think you'll get like 45 out of 50. Every year, there are some groups that just do amazing, amazing stuff, and I wanted to leave room at the top so I can give them 50 points or somewhere in between. And so, typically the average grade in the class on these is closer to like 47. A lot of people go beyond kind of the minimum expectation. But I do have some leeway in the grading on this is kind of the one place where I have more it's less formulaic and I have a little bit leeway of grading it. And I try and do it according to the effort you put in. If you have a lot more work in the data collection and cleaning process, I will understand that, write that in the report, and I'll take that into account in the final grade. But there's some groups that won't end up doing as much and they won't get as high of a grade. I've read a lot of these in the past. I can kind of tell pretty much kind of how much work various things were and try and put that in. All right, so kind of the other things to look forward to, which are kind of very, very essential here. So it's distinct title and names. Okay, so make sure that you put this on your final report. You'll use the same for the posters. Okay, same for posters, and we'll have some sort of site that links to all the posters, and you want to have the same name. It's just to make everything more easier and smooth. Okay, and then make sure you review the problem definition and motivation. This should have been in your project proposal. You can reuse a lot of that. Explain your data. This can be reusing a lot of stuff in the data collection report. Okay, so even though this might say, oh my gosh, 12 pages, you've probably written a number of these things already. Okay, then one thing I'll be looking for, and one thing that will excite me, is if you have a kind of a key idea of what is new, what is exciting, what I could potentially learn about these things. As I'm going through these, if there's something new I've learned, I'm going to be giving higher marks for that sort of stuff. I like seeing those sort of things. Something, or you're comparing. I didn't know whether this technique or this technique would work better. Let me try them. Let me compare them, and let's see. Right? That's a cool thing to highlight, and I can get something out of. That's a great thing to have to kind of put in the report. Okay, and then kind of have a section of what you actually did, and this kind of lets me know the work you actually did. If there was, especially if you think there was, you kind of decomposed it into different students, a different amount of work, or it wasn't quite balanced, then kind of explain that in here as well. Or you could have something in the appendix explaining that. If you think it was even, that's not totally necessary. I'll just, okay, and then in what you learned, it's kind of super important to have these artifacts, kind of charts, plots, examples, kind of math explaining what you did. Just 12 pages of text is going to be more challenging for me to read and get out what you did. Some of you are fantastic writers, and some of you are learning. And frankly, one way to make writing easier is to have charts, plots, examples, and math, and use those to help you explain what you did. You still need to write the text explaining it and connect to those things, but use those as resources. It makes less stuff that you have to write, but it gives you something to explain, something to ground the actual report to. These are super important. I appreciate them a lot. And as you keep going, having these in there. If your report looks a lot like one of these Jupyter IPython notebooks, that's probably great. That's probably a good thing. Okay, great. So any questions? Oh, yeah. So any right. So there's a question on the posters. For the poster, do you want us to use the format specified by Utah research guideline? Let me look at what this says. I think in the past we posted that LinkedIn worked for you. Let me try again. In past, we've posted an example. We'll try and do that. Oh, so this is about kind of logos and stuff like that. What's most important up here is the title and the authors. There's also good guides about kind of, you should do kind of a rectangular poster. In the past, we did them 2 3 by 3 feet when we actually printed them. So I would, let me look at the 4 by 8, the 4 by 3 one that's linked off of there, and see if that one's a good example. What's important is to have like column structure. Oh, okay, yeah. So this one is a pretty decent structure template. The 48 inches by 36 inches is like a pretty decent template. So yeah, it's good to write stuff in those boxes and then have lots of charts and figures in here, but keep it organized so you kind of, someone reading it knows how to go through the flow of here. I'll talk more about this on Wednesday, but this is a good place to kind of start looking at this. Yeah, so this is reasonable. We've linked to this template in the past, in fact, and this one does a pretty good job. You don't necessarily need to list all the affiliations and so forth at this point. It's all for the class, but you're welcome to do that. All right, so I'll talk more about this on Wednesday. Any questions on the final project, final report, which is due on Wednesday, or the kind of schedule for the course? So great. So let's move on with the lecture. So let's see. We're going to be talking about we're going to be talking about PageRank, but the kind of the main thing this is used for is web page similarity. Okay, and so basically as used in search, or as used in as search engines like Google. And so kind of the first part of this lecture will be telling the story of why Google came to dominate the landscape of search engines. And the main thing they did, I mean, one of the two main things they did was they developed this technique and this idea called PageRank. And so this kind of allowed them to identify the important, the important pages on the web. All right, and allow them to present those to the users and to do it in a way which is efficient, right? But to understand why this was important and how it fit into the context, I think it's important to go back and understand, you know, how do these search engines actually work? Okay, and so the key structure is something called an inverted index. Okay, so and so this is like, the idea is I want to do search, so I want to enter a search query, and then I want to return all the similar web pages. So this sounds like a nearest neighbor search problem. And yes, it basically is a nearest neighbor search problem where I enter something and I want to return all the things which are quick. But it turns out, if you've noticed, you know, that can speed things up a lot. But if you search for something on Google, the results are almost instantaneous, right? And this has been true for search engines for a long time. Now, they weren't always, our notion of what instantaneous meant has gotten so like less patient over time. It could be that a search returned in 1 or 2 seconds was pretty quick. And the point is, if they had run locality sensitive hashing on the fly now, or even back then, this would have taken too long. Okay, so the inverted index actually was a way of storing this, pre-computing a lot of the searches. Most of the searches were pre-computed. So there are a bunch of words in some index, you know, Apple, kind of boat, car, and these are stored alphabetically in a list, clearly skipping over lots of words in the search engine. But for a huge number of words, they would pre-compute these searches. And so you would search one of these words, okay? And the index is kind of a pointer, right? So this points to page 1, page 2, page 3. And, you know, and similar for boat, it's going to be, you know, page 7. And maybe there's a page that was about boats and apples. So page 3 is the same for each of these. And so for each page, it's sort of like the, you know, the title and the URL, right? The link to the web page, and maybe some other information about it. And so when you search, it presents to you these top of the pages, right? And what is most important is the top 3. It used to be the, you know, the top 10, which are loaded on the page. Now they're kind of loaded, but now you get these automatic scrolling things. And so they might not actually be loaded until you actually scroll. And probably now 95% of people don't actually scroll down any web pages. It used to be you would bring up the top 10 and you would scan those, and maybe 80% of the time you'd click on the top 10 and 20% you'd go to the next page. You'd have to maybe go through a few pages to find what you wanted. Now these have gotten so good that you actually just see what the first result is, but it links to this pages in a sorted order, okay? And either the kind of top 3 or top 10 are the kind of the most important things here. Okay, and but it keeps going. It'll have a larger list, and maybe it needs to generate more of this kind of somewhat dynamically, but it will pre-compute the list for a bunch of these keywords. If you search for multiple keywords, it'll do a join of the two things, and so it pre-computes this inverted index. And so when you search, then it kind of jumps right to the page that it's pre-computed. And it does this for an enormous number of things. And so, and then there's some stuff it has to do on the fly, right? Where it will do something like some version like one of these nearest neighbor search engines, but those will take longer. But for most things, it's pre-computed. And so like even the query, yes, so the query might be Apple, right? So I might misspell it, right? So APLE. And so I would go, it would probably find this one using kind of the edit distance in between these, right? If the edit distance is close, it would map it to something it has stored here, right? Edit distances in the book, I don't think we got to it in the lecture this year, right? Okay, so this is the main idea. I want to find the web page. So I quickly pre-compute and store all of these things. And so for a long time, search engines have worked basically this way. And they were dynamic to a certain degree, but a lot of it was pre-computed. Okay, but these lists, these are sorted lists. So I still need to compute the most similar pages. It's just I typically do this as much as I can offline, as opposed to at the time. So I can now kind of do these in batch. And so this nearest neighbor queries are like, well, for all these kind of keywords, I want to compute them all at once. And locality sensitive hashing you can handle this, or do other data structures, do all these in batch as well. So it's the same problem. It's just done kind of pre-computed as opposed to on the fly. Okay, so I still need to find, so I need some notion of define most kind of relevant, so web pages. Okay, so the most relevant web pages. How do I find the most relevant web pages with a, say, a query like the word Apple, right? So how would I define the most relevant web page? Well, so the first approaches for doing this is I would take this page. It's got, you know, a title, but it's going to have lots of text here, right? So it's going to have lots of text on the web page. Okay, and so the first things approach, they would take this text and through either doing some k-grams, and I get a min hash signature, or I'm going to do the bag of words, and this is going to be kind of a word, you know, so vector. Then I'm going to have some distance I defined. The distance in this case would be like Jacquard distance. Distance here would be the would be the cosine similarity. Okay, and then I can do and then I can compare these where the query I can also represent as kind of, if it's kind of Jacquard distance, well, it's going to have this, set, which is if I'm using the Jacquard, then the set is only going to be the word apple, okay? Or if I'm using cosine, right, then it's going to be this tall vector, right, which is going to be all zeros, except it's going to have a 1 on the word apple. Okay, so the query becomes the single word, which is important here. And then I just do, the regular kind of locality sensitive hashing, or one of these other kind of other ways of determining the nearest neighbors. And then the ordering of these neighbors can determine the sorted list of the search engine for these web pages. All right, so this was basically how the first search engines of the web worked. This sort of idea is still used, but it's not and this is an important aspect of it, but it's not the only ingredient that's used anymore. Okay, now there's kind of these more complex kind of functions that determines the ranking of these pages. And part of what is part of the reason why this is that this can be spoofed, right? So as soon as these search engines became a big thing, people said, well, I would like to get my web page so it gets indexed by these search engines, right? Before Google, there was Alta Vista, Lycos, like InfoSeek, and they were building search engines in this sort of formal way, and everyone wanted their web page. If I created a web page in the 1990s at some point, and I wanted this to be indexed, highly by these, so if they search for certain keywords, so what could you do? And you can answer in the comments if you want to. What could you do to try and trick the search engine into ranking your web page high? Okay, so one thing I can do is I could take, if I want it to be ranked high for the word apple, I can write the word apple, over and over again in the web page, right? Maybe at the bottom in very small font, maybe the same color as the background of the web page. I just repeat the word apple, 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 apple over and over again. And what does that happen? Well, then if I'm using Jacquard similarity, it doesn't necessarily kind of help. If it's a weighted version, it does. And cosine similarity, well, then I'm going to look much more like the query vector, and I'm going to be more similar. So if I find a common search word I want everyone to use, then I want to use this in the in my web page a lot. And maybe I write the word naturally in text, or maybe I actually just copy it over and over again at the end, right? So these were tricks people used. And so there ended up being this back and forth between these search engines and people trying to index them. They wanted to be useful, okay? And so one of the ways of doing, they kind of combat, well, they looked at things like the title more. And these factored more heavily into these vectorized representation or set representations of these web pages. Or if there are other sort of tags you can put inside the HTML, if you've ever played with this, and so these became kind of more useful. But then people can put kind of whatever they want to be indexed under, they put that in the title and in the kind of the various header tags that you can in HTML. Okay, so this wasn't that great. But then you said, well, if I wanted to be about apples, then maybe I think, I'm thinking, well, maybe I want to put something like the word pie and tree, and like if I want to think about the fruit apple, I think that's what they're after, then I'm going to kind of elevate kind of these values in the search vector as well. Maybe the word apple is still highest ranked, but I put other relevant terms if I'm looking for apple recipes, they're going to be in the search vector. Okay, so I can, instead of just using that single word, I can think of other similar words, and I'm pre-computing this for lots of things, so I can try and figure out what this is. And in the search engine, and they were playing all these tricks to make their search engine better. They can find which pages were actually maybe useful and take words from those. Okay, so, but again, this could also be kind of spoofed, right? If you were, and there were companies out there, I think there probably still are, but there are companies out there that could help your web page be indexed better for certain searches. And so one trick they could always do is they could go and if I'm trying to get my web page indexed better, what I'm going to do is I'm going to say, I'm going to add some stuff at the bottom, right? Maybe in the same color as the background, and it's really tiny font. But I'm going to put stuff in here that's going to help help the index. And what can I put in here? Well, I can search for a term, and I copy the top the kind of the top ranked web pages. Okay, so I will actually use the search engines to figure out how to spoof them by searching for the term I want to be indexed under, finding the top ranked web pages, copy their text into the bottom of my page in small font with the same color as the background, or in some way, and kind of use this to kind of, whatever the search engine is doing based on the text of the page, to use that kind of against itself. Okay, and so this led to things where there was kind of some stagnation in how well the search engines were doing, and they were competing. They were worried about lots of things. They were trying to scale up to this quickly growing web as well, and keep the speed up and figure out how to scale these things. And MapReduce kind of comes into this aspect as well, where also Google made some advances. But kind of there were kind of all these games and kind of these back and forth there. And just using the text on the page itself kind of had these these limitations. There's some limit to kind of how well good a search engine could work by just using the text on the page, because of these kind of ideas of inserting this stuff in. At the same time, there are a couple of other things, kind of other technology which was relevant going on, to kind of keep in mind. One was these idea of these crawlers, and these are still used, kind of used today. And these are kind of these bots that all these search engines would use, because they need to figure out, okay, what is out there on the web? I want to index it and serve it up. I need to pre-compute this. I need to go and look what's out there. But how do I know if there's a new web page? I can't actually spend time in my kind of, you can start out by kind of trying to kind of browse the web all day, and I'll kind of keep track of it yourself, and I'll talk a little bit more about that. But if you want to automate this, you'd build these crawlers, and these are a program, okay, that kind of walks around web, right? So it would kind of read page, kind of, and update its the feature vector on the page, right? So I'm storing some Jacquard kind of min-hash signature, or this cosine similarity, and see, okay, if the web page is updated, I need to eventually it will go and find it, right? You point it to a web page, it updates these feature vectors. But it did something else to find new pages. It would kind of follow these random kind of these hyperlinks. Okay, so a very important part about the web is not just it was a static piece of information, kind of that just listed stuff. It's not just a poster, but it had a link. You click on that link, you go to another web page. So it's one of the things that made the web so powerful. And so these crawlers, once they updated the important stuff for that page, they would link to another page and they would follow those links kind of randomly. There are a variety of ways of doing it, kind of more depth first, cross between that and kind of trying to balance depth and breadth to spawn processes to do this. And it would go and explore the web by just following all these links. And this is how they would discover new pages and keep their indexes fresh, right? So these search engines needed to continually do this so they had the up-to-date information so they would know if there was, my webpage started talking about kind of cherry pie instead, then if you type that in, then it would know, okay, cherry and pie, then my webpage had all the information on this. So it would index on both of those search terms. Right, so I want to update that. That's step one. But then if I link to other recipes, well, then I can go find where I got that recipe from, and maybe I find even better pages or stuff on how to make cool crust, you know, in the apple pie or the cherry pie, right? So so this was kind of so this was part of it as well. So it would read the web pages and they would follow these links. And it was kind of crawling like a spider kind of around the web. It would go and kind of and explore all these web pages. Okay, so this was an important part of this ecosystem as well. Okay, and then so one of the things this enabled is that now my inverted index ranking, okay, the inverted index ranking could use the hyperlink information. Okay, so now if I link to this web page, you know, href, right? If you've ever done it to, you know, if I link to this with pi, right? Well, with the word pi here. So if there's some web page that links to my web page, right? Let's say this is my web page here, pi.com, and I link to it with the word pi. That's probably a pretty good indicator, or that someone else links to it with the word pi. That's probably a pretty good indicator that that's an independent source saying that this web page is great information about pi. Okay. So I can use that word in the hyperlink for more information that is just on the web page. All right, but so you know this was kind of counteracted because then what can happen is these spammers, these you know, either a legitimate company, depending on the search engine's views, trying to set up these spam web pages. What they would do is they would kind of build a kind of a fleet of pages, and you could pay them to link to your page with a, you know, a hyperlink tag, right? So I want to get my page indexed. I can pay someone to create a bunch of these phony web pages and link to my page with that, right? And this sort of stuff happened and still does. Okay, question. So what happens if the page doesn't have any links going to it? How can the crawler find it? Yeah, so there was, you know, this would be a problem. It would be hard to find a web page if no one linked to it. So back in the day, what you would do, you create a web page and then you go tell all your friends, please link to my web page. And if there's some faculty who made their web pages like 20 years ago and haven't completely changed them, who still have a list of things saying, so-and-so asked me to link to their web page, and here are all these links to them. And that was one of the places you got seeded. If you're part of, like, my web page is underneath the School of Computing's web page, and they make sure they link to all of their faculty on there, right? So kind of these kind of, if you're part of a big entity, then hopefully they will get linked to from the School of Computing is linked to from the University of Utah. The University of Utah is a big enough entity. Maybe Google knows to start, or search engine knows to start a crawler there, or it gets pointed to for some reason. They point to School of Computing. School of Computing points to my web page when it gets created, right? So that's often how it works. But if you were like on one of these GeoCities or something, they would kind of have an index of all the web pages that would note to point to all these things. But just buying a domain and not telling anyone about it, you might not get indexed, and that was something that would happen, right? Okay, so you wanted to get someone to actually link to you, and this was an important part of the ecosystem, and it's still, we'll see, it still is important. Okay. So this kind of helped, but it didn't. Spammers had a way of getting around this as well. So it didn't solve the issue of, okay, which web pages are actually important by itself. Okay, I should point out there was another technology here called these like these indexes, and this was an alternative. These are an alternative to a search engine. Okay, so when search engines first became popular, people were very skeptical of them. They're like, this is not how data will get organized on the web. This is, okay, it's kind of cute, it's interesting, but that's not how we do it. We have phone books, right? When you want to look up a plumber, you go to the phone book and you go to the plumbing section and you kind of flip through, kind of AAA plumbing comes first, right? And so you call them because they chose AAA plumbing, right? So that's how we do things, okay? And so there were companies, you've probably at least partially heard of these. So there's Yahoo, and so Look Smart were the two most popular of these. So Yahoo still exists, and I think it's yeah. So every time I've been looking up, it's been dropping, but it's often in the top 10 most popular web pages, kind of out there on the web. It's been dropping slowly over time, but it's been kind of a it's still a heavily used website. So you hopefully have heard of it. So like I worked at Yahoo for an internship at some point. So back when it was still kind of a back when it was still an actually pretty vibrant business, which is not too long ago. And these built an index. They were not originally a search engine. Yahoo eventually pivoted to be a search engine. But what they tried to do is they just kind of built and organized and a curated collection of websites. Okay, so think of this as something like Angie's List, okay, where it's curated. They have some moderation going on. And initially it started by like Google, but like 5 years earlier, two Stanford PhD students who probably spent a lot of their time browsing the web instead of what they were supposed to be doing, and made a catalog of their favorite websites. And they realized a lot of people are coming to their website because they had the best catalog of websites on the internet. And they started organizing this and figure out ways to try and automate the organizing this through crawlers and other technology. But they curated it and they said, okay, here are the different categories of things you might want. And for a while, it was not clear whether this was the right model or search engines were the right model on the web. And I mean, people thought Yahoo and Looksmart were built these indexes like a phone book, but you could kind of run, maybe a search on that page for just keyword kind of text match, string matching. But you could find what you wanted pretty quickly. It had this hierarchy like Craigslist is kind of like this. On the front page, they just have these categories, and you click down, and then eventually you do search and some other stuff. But it was very organized and a hierarchy of what was going on. And it actually was a lot easier to sell, to make money in these sort of companies, because people could pay to be curated higher. Maybe they were mentioned their pages, they were, or to get in the top of the list under a certain category, right? This seemed to make a lot more sense. That's how the phone book operated. This was kind of a very sensible way of doing it. But it's still not, and so because of the spam problem in search engines, this had a lot of advantages to it. They could filter out web pages that were copies of other ones that came on later. They said, look, you guys copied this on the web page, we're blocking you. Or they said, this web page is not really about apples, they're just trying to get indexed, right? They've spoofed it. So they had ways of doing that because there's more human control in what was going on. Okay, and they were looking to ways to scale and so forth. So this was kind of the state of the art when like Google came on board, and they came up with this PageRank algorithm, which we're going to talk about next, right? So PageRank, which kind of changed the way search engines work and made them so that they ended up being much better than previous search engines, and got around a lot of these issues with these spam web pages, and became more useful than what was happening with the indexes. And this kind of took off, and that kind of changed the structure of internet forever. Right. So, okay. So they kind of had these two basic ideas, and it was kind of like use the data of the web to kind of crowdsource what was important. Okay. So there are two main ideas, and so they were that pages are kind of important if linked to not just with the tag, although that helps, but by other important, so by other important web pages. Okay, so if we know which web pages are important, and those link to other important, those probably link to other important web pages, right? If you have a valuable resource that is trusted, it probably links to other important of these web pages. For instance, before ads came to dominate them, these indexes were kind of these trusted web pages. If they link to important things, well, that's probably a good guess that it was important, right? So someone want to build that in. Now, this is kind of a chicken and egg problem, because I need to know which ones are important to say which other ones are important, right? And this was kind of the big conceptual thing, is that this was defined recursively, but I can kind of, if I can bootstrap this, then this really makes sense. So people didn't think about it because they didn't think, well, how do I know what's important to say what other things are important, right? I have to kind of link, this web page to kind of a page is important if it's linked to another one, so, but how do I know the first one is important, and kind of, right? Okay, and so the other thing is that a page is kind of important if a random kind of surfer, a random web surfer who's just kind of like a crawler, like one of these web crawlers, were to find it. Okay, so like was asked, if you were to create a web page and no one linked to it, frankly, it's probably not important, right? If unless people are going there because of you've written pi.com with a skywriter and people are just directly typing that in, and that was, I guess, more common back in the day, then maybe that they would find it anyways. But otherwise, you'd only find it if you're a random link surfing around the web, which I think was even kind of, the web was less segmented back then into like the Facebook world and the Twitter world. And so people went all over to these different pages. And if you were randomly found it a lot, then it would, then that means it's important, right? And so again, one way of thinking about this is if their random crawler, which is kind of taking these random walk from these links, if they keep stumbling upon the page, well, that's probably important. Okay, good. So this was the main idea. And so, if you've been paying attention so far and you're thinking, okay, what does this mean? And you actually managed to see the lecture last week on Wednesday with the Markov chains, you're probably like, aha, I see what's going on here. This is the web graph. The web is a big graph, and we're going to convert this into a Markov chain, and we're going to use this Q star vector that represents what a random walker does, right? And in fact, one of the algorithms we talked about was randomly walking on this graph and just keeping track of which pages you hit the most, and that gives this Q star vector is what's kind of, it's what the second point is saying, right? And it's a link to it by other important web pages. This is this is like the delicate balance. Okay, so if there's a high probability of being this web page in the Q star vector, and you link to another web page, well, then it also has to be high probability of being there, right? This delicate balance says this. This is kind of the random MC kind of view of the Markov chain. We're actually randomly walking around on this graph. These both correspond with this Q star vector of a Markov chain, right? So let's look at this a little bit more formally now. Okay, so the web is a big kind of graph. Okay, G, V, E. Okay, so V are this kind of the set of all of the pages, and the edge is so then let me say edge EIJ equals a link from page I to page J, right? So if I have a hyperlink, this defines an edge. Okay, does this escape the problem with the crawler spoofers you mentioned before, where people would pay others to link to their site? Yeah, so it helps in this. We'll discuss in this problem. It doesn't, there's still some issues I have to kind of explain. It immediately made a big impact, but it didn't completely solve it, and we'll kind of discuss that in just a second. Yeah, so okay, so this is the web graph, and then I can define kind of define the Markov chain on here, and I'm going to get this Q star vector. This is the converged to vector is kind of this distribution, okay, on the web pages. And so this is converting kind of the directed adjacency matrix from edges into the probability transition matrix and taking the first eigenvector of that, right? Is one way of getting it. But as I mentioned, there are other ways of doing this as well. Okay, and so this kind of tells me, so Q star J, if you know, it basically says how important page J is, right? So this is the main idea. If Q star, the entry for that, for the web page J, that basically says how important is that web page. If that value is large, then a random walk will keep coming back to that page pretty likely, right? And okay, it's exactly modeling this concept, which I think makes a lot of sense. Okay, so okay, and so basically what happens is now I'm going to have, you know, ultimately in the search engine, how this kind of at a high level, how this feeds back into, if I have a search and I want to say a page J and I have a term, I want to score how similar it is. And this is going to be some function, which is going to be the text on page J, the links to page J, but I'm also going to include information about this Q star, right? So if I know the web page is important, kind of that goes into the similarity function. It's going to have all the stuff we talked about. It has to do with the text on the page, the headers on the page, kind of what are the hyperlink text that links onto this other page, but also is this a page which keeps coming back to it? And that kind of in a ranked list, this kind of helps push towards the top the pages that actually a random surfer would find that a lot of other meaningful web pages actually link to. Okay, so that's kind of how it shows up in there. What this function is effectively kind of a secret within inside of Google and other search engines. They kind of don't publish it because it makes it harder to spam, and also I guess it's a trade secret and some other stuff. But there's kind of this mysterious function F here, right, which takes in now a variety of this information. But nobly, Google is different because it included this PageRank vector, which they had in some way, at least a rough way to compute using the crawlers anyways, right? So, but then they developed other ways to compute this more efficiently. Okay. Okay, so let's talk a little bit more. Right, so let's quickly talk about how to compute this, and then I want to mention some of these other problems. We have not completely solved it yet, right? There are a couple of other issues we haven't dealt with, including there's still some stuff that some spammers can do to try and fix this. Okay, is the function computed offline before? Yeah, right. Like everything else about these inverted indexes, I completely rank with the keyword everything that's I rank all the web pages ahead of time, and part of this I compute Q star offline. So I want to compute Q star of the web graph, right? And this kind of give me an importance for every node on the web graph, and I'm going to compute this ahead of time. Google would do this. Now I don't know how often they do it. You know, when I started teaching this course, definitely they were doing it most nights overnight. And then a few years, 5 years ago, I know it was like every night they would recompute Q star, right? And that single vector that had a kind of some score of importance that went into every web page that they had cataloged. And they would redo this overnight every night, and it would update their indices in the morning or something like this. Now it's probably done more dynamically and continuously. Right. Okay, but it's a big computation. The web graph is a pretty big graph. Okay, and so MapReduce was one of these technologies developed to help deal with the scale of computing a better estimate of Q star. Right. So one way of computing Q star was to just kind of keep track of the crawlers, right? So how frequently did the crawlers I already had sent on the web keep coming back to a page? Just keep account how many times was that linked to on the pages I visited. And if that, the higher that count, the higher the Q star value. They already had this estimate. As we mentioned, this is kind of just given the input data and a fixed finite graph. This is kind of probably the least efficient way how to actually compute and estimate this. This converges the slowest. If you're if you have these cases where we did this metropolis algorithm where you have a continuous kind of space, then you want to do this because it's more general, because I can't have the linear algebra operation, but these linear algebra ways were actually faster, right? So one way of thinking about it is to buy a big, computer so I could fit everything in memory. We hadn't thought a lot about external memory algorithms for these sort of things yet, or at least these are like these big Cray machines. And then I want to compute eigs of this, the probability transition matrix, trans of this web graph G, right? So compute this probability transition matrix, compute the eigen decomposition of this, take the type of eigenvector using kind of traditional linear algebra systems that were used in these high performance computing techniques. And this was one way they could have done it. Google got off the ground by these kind of fairly poor grad students, and they're like, we can't afford Cray, so let's not do this. So instead, the other way is pre-compute, pre-compute P star, right? Which was this, if I multiply, which is P times P times P times P a bunch of times. Well, this is dense. This is too big, right? It's too much information to store. This n by n dense matrix. N is now every web page on the internet, and it's super sparse. And a web page has about 20 links on average on it. That number is varied, and it's probably grown over the last few years, but for a long time it was not bigger than 20. So it's this really sparse graph that they were talking. But P star would become dense. So it went from basically n times 20 to n times n, where n is millions, right? And this was too much space. So the other way of doing it is Q star equals, set Q0. This is from kind of last night. So the night before, I computed a Q star, which is the value from last night. And then for J equals 1 to 50, which is what I heard was what Google was using for maybe 10 years ago. They were doing 50 iterations of Q J equals P times Q J minus 1. Okay, so I'm updating this by multiplying by the sparse matrix P over and over again. And basically what this did, you had this matrix P, which is very sparse. So if I look at any column, right, this is basically, this is some page J, and any column only has a few links to other web pages. And so that updates the probability to PI prime and PI double prime, right? And so I take this Q J minus 1, right? And I basically, when you do a matrix multiply, you think of translating this here. And so this is for the jth web page, was, this is PJ, this is its estimate of how important it is. I multiply it and distribute it to these here, and I add this up. For every column I add this up, but everything is very sparse. So I can, even though it's huge, I wouldn't actually do the linear algebra. I would write some like C code that had a loop and it just updated the vectors. Or there are distributed ways with MapReduce that maybe we'll get to this lecture. Okay, or maybe at the beginning of next lecture or something like that. Okay, so this is how they could compute it. It was really this iterated thing, and if you know the power method, this doesn't look too different than the power method either. Okay, so this is basically the power method to computing the top eigenvector. Okay, so this was, okay, good. Okay, so just as I planned, so the web graph though, if we're going to do this Markov chain analysis, I spent, 20, 30 minutes that lecture talking about, is kind of this graph ergodic, right? So is it ergodic? Is this property? We could really only use this analysis of Q star if the web graph was actually ergodic. If it wasn't ergodic, then we couldn't trust this. This didn't necessarily actually work. And so the web graph is kind of like this. There are these web pages, these lonely web pages that kind of no one kind of links to, right? So if you're asking, what if no one links to your web page? Well, then it's out here. It's not going to get any Q star if no one links to it. There's this strongly connected component that everyone kind of, people link to each other pretty well. This is the main part of the web. There could be these tubes that go out here or stuff that they link to, but then no one, someone else, this was my web page, no one linked to it. I asked my friend, no one linked to his web page, but he linked to mine. That didn't help too much, right? Stuff that's just disconnected up there. People who don't know how to use hyperlinks, like my father's web page for a long time didn't know how to use hyperlinks, so it had no links on it. But then you could also think of this out stuff that people link to these web pages, but they don't link to anyone else, right? So if I link to my dad's web page and he has no hyperlinks on his web page, well, then what's going to happen to a random walk? It's going to come to this structure and it's going to get stuck there, right? So this doesn't really work. So what do crawlers do? Well, crawlers, they wouldn't necessarily just use the depth first search. They might do a mix of, they'd spawn threads, and if it ended, okay, would just keep going, right? So it might actually look like this. We'll come back to this picture. It's actually a bunch of links inside of here. And if you got to one of these kind of web pages, you kind of got stuck because there's nowhere else to go. Okay, so before PageRank could actually be deployed, these guys were aware, Larry Page and so Sergey Brin, they had learned about Markov chains, and so they kind of knew I have to make it ergodic. Turns out there's another formulation pretty similar by John Kleinberg that was not quite the same, but kind of a hubs and authorities model that also made this kind of intuition around the same time, kind of contemporaries of each other. He decided to stay a professor instead of start a multi-billion-dollar company, but he's done other great stuff as well. So actually no shame there. But so, and then actually Alibaba started around the same time, and they went and did this in China, but it was basically roughly independent, all three of these groups. Okay, they realized that I could use this kind of eigen analysis of the web to do this self-referential was important, but I needed to add this idea to make it so the graph is going to be ergodic. Okay, so can we make G ergodic? Okay, so how do I do this? And there's basically a simple idea. It's not ergodic to start out with, but I can do this simple idea called teleportation, and it's sometimes called, so taxation. Okay, and so the idea is that about once every 7 random steps, about once every 7 or so kind of steps, I want to jump to or teleport to a random node in the graph. Okay, so I'm going to randomly jump to a node on the graph, and so kind of and this might be what a random surfer might do. Follow links, and eventually this links kind of get to a weird spot on the web. I'm like, let me go someplace else. I'm bored. I've gone down into a rabbit hole too far. And they decided 7 was a good number of steps, roughly to do this. Okay, so if you're doing a crawler, this might make sense. You start someplace kind of that you have in your index already. I've got this catalog, so I can jump to a random page. And then I go 7 steps. I collect all the information, and then I jump to another random page. Okay. And so, okay, so how do we model this? Let's say I've got P, which is the probability transition matrix of the web graph. Okay. And so, so I have this, but I want to model this random teleportation kind of jump, which is going on. And so I want this to be, I'm going to model this as about 15% of the time, I'm going to jump to a random web page. So what I'm going to do is I'm going to create a new matrix R, which is going to be, so I'm going to set this beta as 0.15, which is about 15%. And, you know, I'm going to create this new matrix, which is a mix of 2 probability transition matrices. So I'm just going to linearly add them together. And if I weight them appropriately, they're both probability transitions. So the first one is 85% of the time I follow my random link, plus 15% of the time I'm going to do this matrix Q, and Q is going to be basically all ones divided by n. Okay, so this is the whole matrix. It's an n by n matrix. I'm adding together 2 matrices. They have to match in dimensions. They're both n by n, right? And this is and it's basically 1 over n in each of the entries. So that means if I have this kind of Q j minus 1 here, then I look in this column, and this is 1 over n. So I distribute it, the weight, kind of equally to all pages, right? So 15% of the time, I'm going to go this Q thing, and I'm going to jump to a random web page, right? So this is what I'm modeling. Okay, great. So this I can model now with linear algebra, this teleportation process. The problem is this matrix now R is now dense. Okay, so now when I do this, if I multiply Qi by R, this is now a dense process. This now takes much longer to do, but I can decompose this. What I really want to do is I want to say RQI. I'm going to say, well, this is 1 minus beta P plus beta kind of QI. And I can push this QI through. So now this is 1 minus beta P QI minus 1, right? So this part is sparse. I can do this plus beta. And now I know this Q is going to have the same in every column, so it doesn't matter what QI is anymore. I can just create a vector, which is the, I can say this is the all ones vector divided by n, right? So this is now just, you know, I can just directly store this vector. This is a n by 1, you know, vector, which I can just store. I can just add this to everything, right? So it turns out that this process still can be done efficiently, this iterative process. I multiply here, I scale it down a little bit, and then I add on 1 over basically 15% times 1 over n to every one of the entries. Okay, and so this taxation teleportation process, now the graph is densely connected, so it's ergodic. It definitely doesn't have cycles because I can always jump to a random node. It's connected. It has no transient and these transient and absorbing states. So it's ergodic. And it turns out this actually regularizes stuff pretty well too. This makes it a little bit more stable. There are some issues with the stability. If you look at the robustness of these things, this makes it more stable. Use the way to, if you think of this as a stable form of the eigenvector of a graph as well. And this shows up in other parts of analysis. It's kind of like the regularization term in regression, it turns Okay, and 15% is pretty standard thing to do here. Okay, so spam farms are still an issue here, right? So now, so I promised I'd come back to this. Now let's say this guy is kind of your web page, and no one links to me, right? I'm like the comment. I create a web page, no one links to me. I want to get it off the ground. What do I do? Well, what I will do is I will pay. This will be a spam farm. I'll pay the spam farm to link onto my web page. So there's this people who create all these web pages, and then you can pay them to link to your web page. But this only works if these guys themselves have to get these kind of these links onto their web page. I need to get these links onto the spam farm. Okay, so how do I get these links? Well, if you've ever have like a blog with comments open and someone writes a weird saying, oh, I totally agree with you, but you should see what I wrote about this too, and they have a link, well, that probably links, these are automatically generated. It's probably, this is the blog, it probably links to here. Okay, and so this links to one of their spam farm pages, and then they can sell links off that page, right? And so they can still game the system with this PageRank, but this becomes a much more complicated process. They now have to get all these links off these other pages, and it peters out after 15 steps. Right? It used to be before that they could interlink all of these pages, all of the spam farm pages, and they can create kind of a lot of structure there, this ecosystem that would gather a lot of stuff. But because it peters out after 7 steps, 50% of the time, they don't want to have too many links before it jumps to your page. Okay, so this helps kind of prevent the spam pages from being as powerful either. Right, so now there's still so now if this, so if this component here is like 90% of the web, and maybe I can actually incorporate these other pages which don't have as many links to them because they aren't malicious in any way, then this is now 90% of the web, and so most of the mass is going to be walking around in here. It's going to be a lot of spam farms that be much bigger in order to kind of credibly increase the page rank. I guess if they're 10%, then that might be a good estimate of how big those are. Okay, so this helps prevent against spam farms, but not entirely, right? Spam farm can still accumulate a lot of the kind of the random walk with all of these links because the crawler doesn't know whether it's a spam link or not, even if you can immediately say, yeah, that I'm not going to click that, right? I know not to click that kind of crazy comment, but the crawler doesn't necessarily know that, right? So it can't distinguish, and it will still walk there. Right, but so the attack against this is to try and find, so what Google's counter is to search for this structure. So they can search for this structure and other things that kind of structurally occur in these spam farms, which are unusual, and there are certain traits that they have, and there's a whole line of graph data mining we're not going to get into, which looks at this sort of stuff. And they'll search for this structure, and then they'll blackball these sites. They will never jump there on a kind of a random initialization, and maybe not follow links onto those pages if they know it's part of a spam farm. That's kind of violating some sort of rules that they've set up. There's some legal stuff you can do. You can set up a new entity and then link to your pages. That should be fine. That looks somewhat similar here. But if they don't, there are certain rules that they've internally decided this is malicious behavior. And if it's gathering the kind of the page rank vector, making that too high in a way that seems mischievous, they will blackball those websites. And that's kind of been one of the most effective ways of combating this sort of stuff. So you can do it on a small scale, but not on a big scale. Okay, so let me, we're not going to talk about about MapReduce today. I just want to add one more concept before I let you guys go. There was this interesting concept proposed by Google this was, I think, around 2015. And they had this, or maybe some researcher, but yeah, no, this is previous to 2015, but there's this notion of what if we thought certain web pages are more trustworthy than others, right? These are fake news, these are not fake news. Facebook is doing some version of this. I can maybe only teleport to kind of trusted pages, okay? And so maybe if I only teleport to these trusted pages instead of a fully random page, this will make it better. What they would do instead is I would get let's say R is my Q star, from PageRank without the trust vector. And this was Q star from the trusted teleport. And then if kind of the R of a web page minus the trusted value of the web page, if this was if this was large, right, this difference is large, I'm much more likely to get there without going through a trusted web page. Well, then this is I might say this is spam. This is another way you can try and detect it. This was a concept that was coming out now. And there's a notion of trying to do this to automatically say the truthfulness of the web page. This is one way to automatically do it. There's other ways with experts or other things about it. And so there's a lot of concern about this, about saying these web pages are trusted and these are not, and the implicit bias that would creep into here. And that was kind of the thoughts that were creeping around, kind of the concerned people of the netizens of the internet around 2015. Perhaps now that's swung the other way, and they wish we were doing some actual curated ways of doing this more. But there's different kind of classes of curation of the web now, right? There's kind of these, there are these kind of, perhaps kind of, some of it is political, it could be other things as well. But for instance, there are these sites that people on the right side of the political spectrum trust, and they're different from the people on the left side of the political spectrum. And think of that as they teleport back to there, and then they kind of wander out down to links. And if search engines factor that into them, they may bias the way that search results are presented. And there is indeed various biased in ways search results are presented. It's not my place to comment on when this is good and bad, but just kind of let this kind of sink in as this is where some of the issues are coming from. And maybe you think of ways you can combat them by thinking about some of these issues. And now that maybe you understand kind of the complex grand structure of the web, which goes into these search algorithms and end up becoming essential because of these issues with these spammers and spoofers of web pages to really rank the essential thing. But now it's driven by where random searchers go and where attention goes, and this is mixed in all these other issues. So I'll kind of leave it there for this lecture, and then we'll talk about communities and such on Wednesday, and maybe a little bit of MapReduce, or you can look at old videos of that lecture on the web, including one time I gave the lecture outside, which was a mistake. But if you're curious, go to about 2015 or so, and I gave that lecture outside, and that was interesting. Okay, great. I'll talk to you all next week, Wednesday, and feel free to stick around for questions for office hours.